Hi, welcome to episode 15. I just had to look up the number because, as I've made abundantly clear, it's hard for me to keep track. Okay. With that little hiccup out of the way, what are we doing today on this episode? The time has come to start looking at these things. I think we've done enough of this optimization stuff here. Let me just clean up some of the stuff we have left over from that. So there we go. This right here, we do the thing that prints out our current status, so we can see how our state machine looks. And the state machine currently has 65 states and 229 transitions in it, and here they all are right here. We didn't do a full peak optimizer because that would actually be a pessimizer depending on what output level, like what output system we're going to use. So we're going to hold off on that and instead start thinking about some of these things down here. And this will actually be applied after we've made decisions about what happens here. And it might not get applied at all because of that. So what we're thinking about in this section, the notes I gave myself, the things that I asked myself to consider, are basically how to decide between one of two different ways that a state machine can be represented in procedural code, given the state machine we have, and then later which types of state machine outputs, like what type of features we want on the state machines that we generate, right? Like basically the code we generate will have the ability to do support certain operations and not others. Do we want just a basic fast full thing? Do we want something that's resumable? Do we want something do we want two things get generated, one for each of those situations? So we can optimize this more. Who knows, right? But that's what we want to figure out. So it's going to start a little bit abstractly. What would it look like to generate this as just a purely control flow system? I want to just know what that looks like and describe it all out in words and in maybe pictures for you. So if it's going to be in control flow, let's take a look at what. Let's just drop it in like right here. That's some fake code. Our state machine would look something like this. We have the following things need to happen. We want to be able to return a token array, right? But that might not be super possible the way it is, so it'll be more like a token list. And token list will basically just be a thing that lets us allocate tokens incrementally. So that if we, run out of memory in one buffer, we don't have to panic or pause the whole thing. We'll just have to go into like a little mode where we extend the list with another buffer that's discontiguous. That'll just prevent us from having to do any costly memory reallocation stuff. And then we want to do like lex cpp right here, right? And so the input to this needs to be, we need like an arena on which we're putting that memory for this token list, right? This would be like result or something. And it needs like the input. So I'm going to just do the fast full input version first, and hopefully that'll get us enough intuition to expand out to all the other things we want to be able to do, including possibly doing this, including looking at lookup tables. But we're going to do control flow based state machine implementation top to bottom, no lookup tables at all, and fast full input version. And I'm going to write it out roughly by hand to get an idea of what it needs to look like, and then see if maybe by the end of this episode we can get a generator that actually generates something, and then we'll start applying optimization levels. So we basically are doing this up here, takes the hand-built language model that I wrote out by hand, and it applied high-level optimizations. Then I've been inspecting that result as I go and looking at it over here and seeing what my model looks like after each optimization at the high level. Now we're going to drop down to generating code directly. So we're basically going to write the new print function. So the print function is going to generate C code now, and we want to see that it gets up and running and that it's working. And then once that's done, we'll start applying optimizations between this part here and that part there so that we can get some low-level optimizations. And those I'm considering different because of the fact that they will be more dependent on what type of output we're generating, and we might actually want to preserve more than one sort of quote-unquote backend, but they're really just phases. The first phase was sort of generic, and this phase is going to be specific on certain concepts that are not specifically about manipulating the model, at least not this type of model. We might end up having to build alternate views of what the model looks like in the process. Or at least apply specific optimizations to local parts that have more to do with what C code is capable of doing, and less to do with, and what our machines are capable of doing, and less to do with what we want the model to represent. Does that make sense? So, let's start by just getting an idea of what the rough sketch of this needs to look like, and then write hopefully the first generator that'll do, we're going to start with this and this as our pair of things for now. Right, so we're going to do that pair, but we're also going to support the idea that we have, so basically like the implementation, let's do it like this, control flow, features, fast, full file lex, and then feature resumable chunked input resumable and maybe we want to explore the alternate implementation of lookup table optimization of the lookup table accelerated version. And if we're going to do that, we want to think about, can we isolate the state machine into small lookup tables? Maybe we want to hybridize these implementations. Maybe we want to hybridize these features. Maybe we want to keep things bifurcated into two different options at different levels. We'll figure that out as we go. So the first one we're doing is just this pair here. That doesn't bring up any of these complications, and we don't have to pay attention to that. So what does this look like then? Well, the way this code is basically going to work is we're going to say when we enter, since we're doing the full thing, why don't we just treat each state as like a label we can jump to, right? And so let's look at the next state. I'll just get a couple of examples here. Identifier, white space, backslash, I'll get a couple more. Operator or f number dot. Operator or comment slash. So each of these is a state, and what we do inside a state is we're going to consume the next character, and then flow to the next state after that, right? So why am I doing this as labels instead of like a switch or something? Well, the point of this idea here is that if I did it with a switch, that would mean that I'm storing my state in a field that I then use to figure out where to go at each stage. And the question is, what amount of shared code would I have then, right? So the idea is doing this, right, like this, would be an alternative idea. So there's like the root case, there's the identifier case, etc. And then if I'm doing this, like we'd say like state code here, then I have the advantage that I can write this as a loop, so that the way I jump to something different is I change the case. So I would be like state code equals root to say that I'm jumping there. But then I have the ability to put some shared code here and here that executes every time I go through the loop, right? So disadvantage to this is that the switch will require multiple instructions of computation to figure out where to jump to, whereas this can be direct hardwire jumps, right? So this, we're spending extra time figuring out how to decode runtime codes into jump locations. Now, in a cool world, what we would do is we would actually be able to say that this isn't really how this works at all, that this is more like we have these things called labels, And then a state code would be like this like label type thing like this. So we'd be like state equals root to begin with, and then we'd be like go to state, right? And state would then be a variable that literally contains a pointer to code, and this go to is just a thing that's reading that. We don't live in that world, so we can't have that feature. We have to put up with the fact that the switch is going to slightly complicate things because C just doesn't have any good way to encode that idea that we store a pointer to an instruction inside of a function, right? So that we can jump specifically to it. So if we wanted to, we could leave these side by side and compare what different things look like in each case and figure out which one is better for us. So if we're doing the first one that I wrote, which is the second one in the ordering now, the next thing that would happen is we look at the next input. So before anything else happens, this version would say, hey, let me get my putter look like this, and I'll have the one past last putter, which is just what you get when you take the beginning position of the putter and do that. So if we ever get putter to this point, we're done. We've consumed everything and we stop running. So now, what we want to do is whenever we enter into a state, we have to write the code if the putter equals the one past last putter, go to, like, you know, end or whatever. And end is just lives down here and is how we get out of everything. So all of these have to have that duplicated right there. So why do we need that? And why do we put it at the beginning of this handler? Well, we need it so that when we have reached the end, we do the end. And we need it first because it's possible we get an empty string, and this is the structure that lets us do that. Now, maybe there's an optimization to have here where this doesn't go first, it goes later, and we just check to see the input size is not 0, and if it is, we just skip to the end right away, right? So if we have to, we can do that. But one way or the other, we kind of need to put this everywhere, and putting it here means that if we didn't put it here, then what would happen is we'd have like some condition gets met, and then we'd have go to identifier, but before that we would do this check, right, go to end, and then we'd have some other condition right here, and so we'd have the second problem that even if we do avoid doing this check here, we would probably end up having to do it here. So we'd be saving ourselves one goto in exchange for doing this code many more times, right? Duplicating out the code. So there's like a code size versus speed trade-off that's happening here. And I'm preferring the code size option for this one because we're talking about the cost of one extra jump. It's just not going to be that big of a deal when we're parsing big files, right, that we have an extra jump instruction to shrink the code down a lot. So I'm going to say that we probably want it structured like this. Now, in the other case, what would happen is that would reduce even further into something that looks more like this. We would still have the same structure right here, but now we're talking about putting it in literally one spot, and then we have this loop, which is essentially saying anything that happens at the beginning of every state actually happens here, and then we figure out which state to operate on. There's not really a good way to get an in-between on these two things. We have to pay the cost of this extra work to do the switch here, and we have to pay the cost of duplicating the code out here. If C was a little bit more expressive, what we would do is merge these by saying we do want this structure, but we want the switch to not be costful. We want the state code to be a hard jump, and we can't do that. So I'm not sure what else to say. We have to pick one of these two. So pluses and minuses all around on that front. Next up, root would need to look at what comes next. So actually, the first thing that it shows is that it does an end of file handler. So what actually happens is end is itself a handler that does some stuff. And when we reach end, we do that. And since we're doing full file, we will always eventually reach end. So there's no, nothing else weird going on, allowing this to flow out. We don't need a way for this to exit separately or anything. This can just always be there. We don't need to skip it. We don't need a way to do anything. It's just, that'll be fine, right? So if we do reach the end of the file, we determine that right here. We say consume, which means what? Well, it means so this is essentially a condition check, right? It's found out that this is the condition we're in. We're in the end of file condition. And so now it's going to go, okay, we're in the end of file. You need to do a consume. Consume looks like this. You increment putter by 1. That's on the root. There we go. So you've reached the end of file. End of file says consume, emit. So we need to figure out what emit means at some point here. And then it says go to root. But we wouldn't actually go to root because we need a special case handler that says, I guess what we're actually going to do is say that it kind of is more like this. And then there's not a handler here. Right? That's actually what's happening. So if this is equal to that, that's actually not what happens here. That's if this is equal to that. Because in here, if putter is equal to 1 pass last, that actually needs to have specialized behavior. Sometimes we'll output and like Lexer errors, other times we will output nothing at all. One way or the other, when we see that end of file, we have to potentially do different things depending on what state we're in. So we end up needing this anyway, right? Because this is actually not the thing. So it's still a case that this ends up duplicating out some work. It's just what we thought it was duplicating is different. So this still has to duplicate one more thing than the for loop, except not really, right? Because now we have a distinct advantage down here that we don't have up here, or maybe that I don't see how to have up here yet, which is that this is a lie. We don't actually need to do this because we know that a consume happens here, and we know that when we go to root we're going to trigger this, so we could just shortcut this whole process and shrink this down to this, right? This would technically do the correct thing, with the exception that we probably want to make sure we still do putter plus equals 1 here. So that we are emitting the token at the right position. Although, admittedly, I'm not sure that that's actually true either, because I'd have to spec out what I actually expect the end of file token to look like, but I kind of expect the end of file token to have a size of 0, not a size of 1, making it look like there's a character past the end of the file that isn't really there, right? But I don't know, maybe this is fine, and the correct way to spec it out is to not let end of file be a 0 size token. Uncertain. One way or the other, we could shortcut that. Could we do that up here? Because the point is now this still has to be spammed out everywhere, but anywhere where we have the handler that checks this condition, which is going to be everywhere, everyone is going to need to do this check. It can just say that we don't actually check to see if we're at the end of the parse. What we do is we check to see if we need to handle the end of file input, and if we do some work, and then we go to end, right? And by go to end, what I mean is we are finished. We don't do any more work. Up here, could we do the same thing? So here, what we would have to do is say, if we in every case, yeah, here's what would happen. Is in every case, we could do that same idea, but now we're going to have to put that everywhere. Everywhere we go, we're going to need to put one of these handlers in, so now this doesn't have an advantage because there is nothing here to share among cases. And I don't see any way it could because these handlers can be different. And this optimization here that prevents having a handler here and then a generic handler here invalidates the idea that we have the ability to share this handler across states. So far this side is winning by 1 point. What's next? We want to model a few more of these behaviors. So if we see any of that, we go to identifier. So how do we know if we've seen any of that? Well, it's kind of a little bit tricky, and this is where having a low-level optimization scheme for control flow is going to be trickier than having a scheme for lookup tables. But for this, what we basically are looking at is worst case scenario. We build out something like this. If putter equals, and then it just starts going through all the things it could be, A, or putter equals B, etc., etc. So this would be kind of bad because we would end up having all the way through putter equals underscore for all the things that can start an identifier, and then on top of that all the things that are in the Unicode range or the UTF-8 byte range, right? So it'd be pretty huge. And so really what we would want here is something that figures out how to optimize that down. Now that's a little bit of extra work we have to do for control flow. For a lookup table, it would just be instantaneous. One option would be to instead of trying to find a small number of instructions that would give us this result and then turn that and represent that by C code, we could also just add in a one-time usage lookup table right here that's like table identifier case table, right? And then it just has ones and zeros here. This could be a B8. Right, it would look like this. Furthermore, it wouldn't necessarily be that hard to find the optimization. We could start by looking at this table and pulling out large ranges and finding good ways to represent those ranges as either as sort of a compressed series of ranges. In other words, if we find the smallest number of ranges that it takes to express this table, and not by ranges of just ones, but also we could take a range of ones and then poke out 1 0 so that you don't need two, if you have the idea of nesting ranges, you might be able to save something there, although I don't know if you would. You'd have you check if something's in this range here, and then if you have one thing you want to poke out, you say but not this, right? And then if it's a bunch of things you want to poke out, you end up having a lot of but not this, but not this, but not this. And for each one of those but not thises, if you had done it as a bunch of ranges as ones, you would have had two comparisons on either side of that thing you poked out, rather than having one comparison for each thing you're poking out. But as soon as you have anything where the range of zeros is larger than 1, you wouldn't get anything for that, because poking out one at a time would actually cost more checks than just saying split this into 2 ranges of 1. So there's options here to play around with how we do this check to make it fast, but it's something we would have to work out how we want to do, right? And then the next thing we would have is, so we've done this check here, we have determined we want to go to identifier. So we do a consume, which says read that thing that brought us into the identifier thing, and then go to identifier. And the go to is correct. It's always going to be the last thing we do, and that takes us to here. All of that would be true of this one up here as well. So there's no difference between these two things in this respect, with one exception, which is that the state code now equals identifier is how we express this instead of the goto. So again, we're not actually getting any benefits for doing this, but we're also not losing anything that we didn't already lose. The only thing we've lost so far is that we're paying for this cost of the switch, and that's still true. Nothing else has gotten worse on this side, so it's still down by just 1 point. Okay. What else can happen here is we see any of these individual characters. So again, this is gonna just look like this, right? So if the putter equals L, and you can start to see why I was thinking about poking out singular things here and there. If the putter equals L, if the putter equals R, if the putter equals U, and there's all these different things that can happen. None of this would be any different from what happens up there. All of these are putter plus equals 1, flag field or equals something, or else it's either that or it's either that or it's like this. Right? One of those two things is happening here and here. Whenever we do a flag set, depends on what parameters. If we're setting it to a 1 or a 0, and which flag we're setting would determine what this is and what this is. And then we go to like pre-L and so on, right? So again, no difference between what happens here and here, except that this would become setting the state code up here. So we haven't actually lost anything yet from any of those things. So where are some things that might actually behave differently between these two? So I need an example that reveals new differences that we haven't considered yet. So one thought that occurs to me is that in either case, there's a weird little optimization we can do where, for instance, if we look at this root state, there are actually two things that align really well with each other. The largest case is this one, so it probably wants to be the else, right? What we could do is, instead of having to do all this work, just say, hey, if after we've checked everything else, nothing else works, this is just the else situation. Right, and that applies in both cases. But what does not apply in both cases, or maybe it does. Maybe it does. We'll just take a look at it though. So this is the final case, and we're saying that look, we've trusted the front end to assure us that the states are the set of possible cases is completely covered in every state. Type checker will, combined with the optimizers, will work to make sure that happens. So the final one we test for is always going to be a freebie. We know that it is the one we do. So whatever is the most costly to check in the control flow case, we can't do this with a lookup table, but with a control flow setup, we can actually just not even do any tests. All the other tests have failed, so this is the one we do, right? So what that means is, if we get to this situation here, we don't actually even need to do a go to identifier. Do you see this? We could then say, whatever is the last case here, not only do you not have to do a test for it, but you can make some small optimizations by saying, whatever the last case is here, if that's the next case you do in the layout of cases, then you can just flow into it for free without doing a jump. So the generated code wouldn't have a go to there, and it would just go straight into this if as the next instruction, rather than doing a jump there to the next instruction, right? Hopefully that makes some sense. But that also applies here, because that just means that if we want to do a fall through, you just take that out, right? And you get the same exact thing, and then this here can just be the else case in the same exact way. The only thing that is maybe kind of neat about this is this is a bigger win here, because now we don't need a state code. Except maybe we do need a state code anyway, because if this doesn't consume its input, or rather if it assumes that right now it's fine, and it will one way or the other figure out the next state code correctly, or flow into it correctly. But if we were to make this resumable, this would still need to happen. So at best we can maybe remove this in the full parse case, or the full Lex case. And what have we won for that? Well, we've won the ability not to pay this consequence on occasion. So it's not really a win. It's a win on both sides, and it's a bigger win for this, but it's not a big enough. It's a win that occasionally makes up for the negative that we've already counted against this case, or against this implementation. It's not a positive that cancels it out completely. So the negative still exists, and that positive isn't so big that it wipes it out. And that positive also gets applied here anyway, so it's not like there's an occasional place where we get really free stuff or something, right? Both cases get that free stuff is the point. Let's see, other things that go on that might be different between these two. How we test for cases would be the same. So once we have decided what state we're in, how we test this stuff is all the same. The only things that ever appear like they're going to be different are how we determine which state we're in, and what happens when we go to another state. So here is one thing that is a benefit of this mode. This mode up here is required if we want it to be resumable, right? So as I was saying, if this is resumable, we couldn't get rid of this because this might yield the state machine for now, and then when it resumes, it needs to remember that it got here, even though it fell through to it originally. Its state code can't just stay as being root, because then it's going to think it needs to do root again when it actually needs to do identifier now. If we did this, we'd have a bit of a problem on our hands, because now we need a way to turn a state code into a location for the purpose of storing where we were at and re-entering it. Now that's actually something we can do. We would end up having to add an initial switch right here that says switch on a state code, and then if the case we see is root, then go to root, right? So we would link up the state codes to the labels by doing this thing, right? And so this is actually going to cost us just the same as this with an extra jump. And so we're paying this price once per re-entry instead of once per time around the loop, which is what happens here. There's another way we could write it all, though, which is we wouldn't even have to necessarily complicate stuff this way by just saying, let's imagine it's more like this. And so now it's the same thing as we had before, with the labels pulled up like this, right? So now what we're looking at, we say, okay, we can still use gotos to transition between these things, but we have this slightly confusing problem, which is we still would have to stick state codes in right here every time we did a transition. So when we transition to identifier, we would get something like this. Right? So now we are storing the identifier like we have to up here. So the fact that this is storing a state code is not saved for the resume case, but it is saved down here for the non-resuming case. But we still don't have the problem where we have to rely on a loop. We still use gotos to get these in the meantime, right? So again, it doesn't, as long as we can't find anything to share between them, this is strictly inferior. We need to find something that's the same about every single case if we want to have this win. And I'm not sure we're going to find something like that. Nothing else about these states is really the same. At least not when we're looking at the basic stuff. So let's look at a couple of other things that are important. One thing that's important is when we go to do a lexeme check. So lexeme checks are whenever we have an emit rule, we can have essentially like a keyword emit rule. And so let's take a look at something like that. So identifier does this. So let's look at the identifier. The identifier has an emit rule. So let's code out what the identifier says it does. The identifier, first of all, has 65 possible inputs that cause it to finish. So let's say if we have an end of file, that's probably one of those. There's some other checks that happen here. If we see a space, you know, if we see this or this, etc. If we see this, then we are going to go to root, state code equals root, and you know what, there's actually kind of an argument to be made that we could do that differently. Instead of having the state code get set on the transition into it, we could put this here, and this actually would reduce the code size, and this is a case where this can't reduce code size and this can, which is an inversion of what we were even saying was possible before. Now this one is saying, hey, the way I remember my state code is that whenever I enter into a state, I store it, because the way I enter into states is not by reading from the state code. I only read from the state code once on initialization, and then I don't look at that again until the next time I enter from above. This is saying, hey, I read that every time, so you have to change me in order to go to the right place. Therefore, every state transition has to have one of these setters for this thing, whereas here, only each state needs to have a setter for its state code. And again, we wouldn't need this at all if we weren't trying to make a resumable version. Alright, so I'm still looking for any reason why I should prefer this at all, and I'm trying to sneak up on one here, because there might be some stuff we can share if we look into some of the more complicated details. So When we go to do an emit on the identifier, we don't actually just do an emit. What we actually do is we say, first of all, this says go back to the identifier. You know, there's another cool thing we could do, which is skipping that state code setter, so that this can set that, but then if I'm already in the identify state and I know that, I can avoid setting it again by just going like this, right? So I'm jumping into here from myself. And I avoid the extra instruction that it takes to store that constant right there. And then we go, okay, do these checks again. On the new putter we're looking at, this thing here that goes to root also has an emit in it. So the full implementation of what this does is identifier, when it does not go to root, increments its putter by 1. And when it does go to root, it first does an emit. Now before it does that emit, it has to do keyword checks. So we have to actually look at the emit rule to understand everything that it's going to do. So let's take a look at the identifier state. And you can see here that instead of just emitting, it actually is doing these keyword check things. So first it's going to look at if the PP body flag is set. So it's going to do something like if flag fields, I want to check if that has a flag, you know, is PP body flag or whatever. Doesn't matter, this will all be generated code, so that'll be a flag that it knows the value of from out of the model. It'll check this flag field and it'll say, okay, if that flag is set, then we want to do a key check on this. So what we are doing now is we're saying we need to have the lexeme. So we could look and say, hey, we have a chain of these things coming here in this handler. Before any of that happens, you know, this is an optimization that applies no matter which implementation we do. The two we're comparing or the lookup table, we need to have a way to say grab the lexeme, right? Current lexeme or something like this. So the current lexeme is everything from the point where we left the point where we did the end of the last token that we emitted to the point we're currently at. We want that as a string. Now, since we're looking at this right now as a non-resumable thing, the entire input's right here, and that's just a contiguous range, which means we can just store that as a state. Once we want this to be resumable, though, there might be a reason to prefer this, because now there might be some work that has to happen here, which is worth us taking a look at now. How would we do that part if we wanted to have non-contiguous ranges? Well, the problem is that non-contiguity is going to imply that the memory that we're passed in isn't necessarily contiguous with the next piece of memory we're passed in. So a token that straddles the boundary can't be read as just out of that memory. We'll need to remember each character as it comes in, or remember the chunks of the lexeme separately and put them together when the time comes to look at it. The next thing we're going to need is we're going to need the ability to deal with the fact that it's possible that the memory that came in previous chunks won't even necessarily be valid anymore. It might get overwritten with the new memory, so not only will it be non-contiguous spatially, it could also be non-contiguous temporally, right? We might not have the whole file loaded in at once. We might have done the first chunk, evicted that chunk for the second chunk, and then done it, meaning that whatever we did to remember the full lexeme has to actually be a copy of the lexeme, because, you know, I mean, technically speaking, that's two different features. There's chunked input, and then there's chunked spatially chunked input, and then there's temporally chunked input, where this means that the memory is all going to be in memory at the same time. The data is always going to exist, and we don't have to make copies. If it's temporally chunked, we need to make copies, and we could potentially make a different version for each of those situations if we wanted to, or make one for temporal or one for spatial only. I don't know. Point is, if we were going to try to handle the worst possible case, the hardest possible case, I should say, that we have a temporally chunked input, which might be a possibility for 4coder to handle if we want to do something like someday handling gigantic text files, although lexing gigantic text files might be a questionable decision. But paging in parts of a text file at a time for giant logs and stuff could happen, and that would require temporally chunked input if you were going to try to lex it. Again, questionable decision, but maybe if you're doing a really simple lexer or something like that, it would make sense, possibly. So, how would it adjust if it needed to be that general? And again, what we could also do is to say that there are restrictions placed that aren't temporal chunking, so it is spatially chunked, or rather it's temporally chunked, but that the caller has to follow certain specific rules about the boundaries between text, so that not every possible chunking is valid, so that it's easier for this thing to be optimized, right? There's all kinds of options. But I want to explore what the difference is between these two things in that worst possible case, because that's the last thing I can even think of that might give this any leg up. And if it can't compete with some kind of advantage in the worst possible scenario where it needs to deal with temporal chunking with any granularity of the chunks and no restrictions on where the chunk boundaries lie, then I'm ready to declare this out and this the way we want to do it, right? The idea is, can we take advantage of the shared space right here? So the way we would take advantage of the shared space right there is somehow, as we are going, using this to track where we are in the chunk, right? So what we haven't considered yet is when we're doing chunked input, who's keeping track of when we reach the end of the chunk? So this would become, instead of input, this would be like chunk.stir and chunk.size. And when we saw this, it would not mean we were at the end of the file. This would instead get written to mean something more like, if this has happened, I see what's going to happen here. So if this happens, then we want to go to end without doing any of these handlers here, and then this becomes like a special, somehow we have to check condition end of file to do this part, right? So point is, when this is happening up here, what we're doing is saying, hey, during the chunked input situation, every time we go through the loop, we want to see if we have reached the end of the chunk. If we have reached the end of the chunk, then it's not going to be possible for this next state to read its next event, and therefore we don't want to go to end. Or rather, what we want to do is say, if is EOF last chunk, then condition EOF equals true, and go ahead with that, otherwise leave and wait for the last chunk later to come in, right? It'd be something like this. So this would work there, in this situation like that. Then the other thing that would have to happen is we would want to keep track of every time we advance the putter, saving that character out to a buffer that we are using to track the identifiers. Now, that part is a little bit questionable too. It's kind of like, do we need a fixed size buffer and that it wraps around? Is that what we're going to do? Or are we going to use a buffer that is sort of a linked list buffer like the token list is, so that it never runs out of memory and can be reassembled eventually when the time comes to check the lexeme? I don't know. And furthermore, whatever we choose to do, is it actually easier to do it this way? Because the time when we know that we've advanced is right here. So during the consume, we have the opportunity to say, before we do a consume, it'd be something like buffer input putter, and that way we can read the lexeme out. If we wanted to avoid this, what we would have to do is we could say, look, every time we come around here, if we don't want to spam that out to every location where the putter advances, then instead what we're doing is saying do this, but we now need to make sure that there's like no shenanigans going on where this could potentially be, how should I put it, a duplicate character, like that someone didn't actually read this, and second of all, that even if they did read it, that they wanted to like emit before they counted that. So the fact that something got a buffer doesn't necessarily mean that it's part of the lexeme yet, and so we'd have to do a lot of complicated checks to make this work, and so we're paying a cost to keep track of if the putter has advanced by doing something like this. Right, so all of a sudden now we're keeping track of this information, which is not only, yes, it is shared code now, but it's shared code that didn't need to exist if we didn't try to share it. You know what I mean? And one way or the other, this is probably going to be a function call, so it's not like we're actually reducing code duplication that much either way. It's hard to say. It's hard to say. I mean, one thing we could do is say that this part doesn't have the job of actually doing the buffering, that it happens here, but it does have the job of like ensuring the buffer has memory. So this could be like ensure buffer has memory every time we go through the loop. So there's one spot where we do like, hey, grow the buffer if necessary with another chain and a link in the chain, and then when we go to do the buffering the actual like something like save input to buffer, this just has to write a character and can get to freely assume that that will succeed because this up here is ensuring this, right? And so every step through we do a little bit of logic here to ensure, but really we weren't always going to be advancing this thing here, and anytime we weren't going to advance it, we are doing this work twice essentially, right? Down here, what would happen is we wouldn't have a singular location where we could do this stuff. So what would it look like? Well, as it's doing its chunking, this it can't assume as an end of file condition necessarily, but all it has to do is say, is this a last chunk? And if it is a last chunk, do that. Otherwise, it would go to like, maybe set a flag that's like, I mean, and it probably wouldn't set a flag. It would just go to end and be like, okay, we got to the end of the chunk, nothing left to do, but we remember that we're in the root state, and now we go to end. Better yet, we can just do this. We couldn't do that here because the handler needed to live down here, so this actually has extra go-tos in the generated code now. This has the cool advantage that we are taking advantage of structures that already had to exist anyway. So really the only thing that changes is we have to add an extra check for this last chunk thing, and this has to do that last chunk check as well, except now we're only doing that last chunk whenever we've actually got to begin a state, whereas this is actually going to have to do this sometimes in redundant situations. Okay, so our answer has arrived. This is just an inferior setup. So the last thing that we had to consider was, what about this idea of ensuring that the memory is big enough to advance, right? And the problem that I was kind of foreseeing was that maybe the code that makes sure we can always buffer the input is a little bit big, right? And so having it in more than one location might be troublesome. And the exchange for shrinking the code down by putting it in one place is that it's going to run on occasions when it doesn't make sense to run it. However, there's actually another way to look at this, I think, which is when we get an input chunk here, we can initially prepare enough memory for identifiers right here. Now this was true of the other one too, but now that I think about it, what we really need is just like some scratch, right? So if we have, I don't know if I actually have a thread context in 4coder. It looks like I don't, so I'm going to just say scratch. If we have a scratch here, then we can say, look, whenever this thing comes in here, this chunk here, well, I guess that's the problem, isn't it? It can't be on scratch because it's not necessarily going to be all, the lexemes could cross the boundary between there and there. So the more important point is that it's not that it's on scratch, it's just that we could say, look, our buffering space, ensure buffering space just needs to grow by the size of it. So we end up having buffering space that's always big enough for whatever is coming in. And it turns out that when we go to grab a lexeme, that we have, you know, the chance to clear that space. Where is grab lexeme? It's in here somewhere. When we get the current lexeme, if it turns out that there's a lot of extra space in there, we have an opportunity to shrink that back down if we even care to. Maybe another option, instead of having this gigantic amount of buffering space, would be to I mean, it doesn't necessarily have to be that costly to expand the buffering space. So what could happen is we come here, it's time to, where is the thing that does the right to buffer? I guess that would be like anytime we do an advance, right? So here you wouldn't do it, you wouldn't apply it in this case, but in this case you would apply it, which is you want to like save input to buffer. And the problem I was having before is that this code might get really big if every time we use save input to buffer we also have to check that the buffer is big enough. So the question is not how do we, like, can we figure out the maximum amount of memory we could possibly need so that we can get it up front. It's just, can we figure out a way to guarantee that we've grown the buffer without having to stick a gigantic amount of code in front of every time we write a character out, right? And I guess that the real answer is that it's actually not that difficult. What we actually have to do is say that there's an escape clause. So what will happen is when we go to write this, what we basically would have it do is say if room to buffer, well, first of all, it would be like save input to buffer. And so up here we would say ensure buffer space available. So we've ensured there's at least one character space worth, so we can always save right away without thinking about it. And then we would do this work here, and all we have to do is say whenever we enter into a state, we already are doing this thing where we're going to set the state code, just do an escape clause here that says, okay, when you enter into a state, you need to check to make sure you have enough space, right? So you could just do ensure buffer space available here, right? In fact, we wouldn't need this then. So this will get duplicated on an order of once per state instead of once per handler. It's still happening just as frequently. It's just only happening in, it's organized in such a way that we don't have to duplicate it out to all of the putter pluses. That might be the right way to do it. We're ensuring we have space available here so that if a write happens anywhere in this handler, it will work. And then when we transition, the next transition will do this again. And that loop we were looking at before had the same quirk, which is that it does this every time. If we feel like the cost of that is so high that we can't bear it, we will have to look at it from a different perspective. But this is what it would take to get fully temporally independent chunks with no restrictions working, is I think something like this. I mean, the other option would be to not allow keyword checks to be a part of the primary pass and to do them as an actual secondary thing, but then you still need the ability to query the value of tokens, which I guess you wouldn't have. So there might be another way. The other way might involve doing some stuff that I hadn't considered before, but if we have the idea that as we read an identifier, there's this like fixed size thing that's, I don't know, we'll just make it big and call it like consume status, or yeah, we'll do a little keyword consume status, right? Then all we have to do is say this gets an initial value that we can predict, and then we have a way to say, rather than saving anything to the input buffer ever, what we instead do is we say update consume status, right here. And that's just a thing that operates on that consume status and this. And then all we have to do is make sure that every keyword in the table uniquely hashes to something given that its size, right? So we have a little bit of a problem, which is that we wouldn't be able to tell, like, an identifier that doesn't appear in the keyword table would potentially collide with this and look like a keyword. So we would still need some way to prove that it's the right word that might not be possible. I mean, we could just go for like crypto hash and then say, hey, as we're doing this, we're betting on the probability being so high that we don't get a collision that it never will matter, but that's going to be way more expensive than what we want to do. So, no, I don't think this would actually work. Maybe at best what we could do is I'd introduce an entire keyword like Lexer that is isolated from everything else, so that when it comes time to start parsing an identifier, it actually doesn't go to a single identifier state, and what we generate is a whole state machine unto itself, but it's isolated in such a way that it doesn't complicate the rest of the Lexer optimizations, right? Then what we could do is sort of similar to this, which is have a state value, right? This would just be basically turning it into a state machine at that point. Have a state value, read a character, update the state value, and then if it ever reads a character that makes it not a valid Lexer identifier, the state would reflect that, and as long as it's a valid keyword, it would continue to advance down. This would basically be the same as our operator parser, right? We could just reuse the operator parser to create keyword parsers and then make sure that they get isolated in a specialized way. That would mean no buffering for anything having to do with identifiers, but we still have an additional problem on top of all this, which is even if we don't buffer any of those things, we still have to buffer delimiters. Now, the nice thing about delimiters is we could technically say that they have a maximum length and they wrap. So actually what we could do is say that when we go to generate this thing, that's all we need. That's it right there. I found it. I found it. So there is the way to do this with a fixed size buffer. We would just say this is like our buffer space, and that buffer space just needs to be a certain size. And the way we determine what size it is we look at the longest keyword in the system, right? And we also say, look, our buffer space is also going to be used for delimiters, so delimiters can be at least 32 characters. The longest keyword we had is blah, whatever, so maybe it's like, it turns out to be like 40, right? The longest keyword possible has 40 characters in it. Then what happens is we just use this as a cyclical buffer that every time we output a character, we output it in the next spot. When we reach the end of the buffer, we go back to the beginning, and we start inputting at the beginning again. And, you know, there's all kinds of ways we could make that work out cleanly. And then when it comes time to grab a lexeme, all we're doing is saying, hey, step 1, does the lexeme, like the length, we can keep track of what the full length is. The length is just increments by 1 every time. So we know the length of this thing. We could also just say we know the putter value when we started getting this token to where we are done now. So the previous token's end position to our current position, that's our length. We've got the length. If that length is less than the size of this buffer, then we can pull that thing out. If it's longer than that, we don't know the lexeme, but we also don't need to know it because we know it doesn't match anything in our table, right? So in that case, we would have a thing that's just like, okay, this is too long, so the current lexeme thing would return kind of like a code that goes with it that's like current lexeme equals current lexeme, and then what we have is like if lexeme fits in buffer, do this, right? And if it doesn't, then we know that it just goes to the fallback case. So here we go, it doesn't fit in that buffer. Then we would go to the next one, does it fit in this buffer? No, but this one has a fallback case. And so then we know to write out a token right here. Right? That's all we need. That's all we need. We don't need to know the lexeme in all possible scenarios. We only need to know the lexeme. We only need to know like the details about the lexeme for a particular maximum length of lexeme. Anything longer than that, we can just say, hey, that's too long to match any of the things we were going to test it against. We're not doing anything fancier with that than that. We're just trying to get the lexeme so we can compare it against a table. The longest thing in that table sets the maximum buffer size we'll ever need. Right. The only time we ever pay the cost of reassembling that thing is when we decide it's time to do an emit. And emits are going to be expensive already anyways. Emits are where we do things like potentially expanding the array of token, or the token list, writing out all the details of a particular token. Emitting a token is basically where we get interrupted for a moment, and we'll do our best to keep it small, but like in cases where we have an identifier, we'll do even more work, right? So we parsed an identifier, we know we got an identifier, we just need to find out if it's a keyword or not. Well, we'll just do this amount of work here. We'll grab the current lexeme by reassembling it out of the buffer if the current lexeme is valid at all. If it's not, we'll just make a flag set to true that's like, hey, we took a look and the size is too big to match anything in any of the tables that it's going to match against, so don't even bother. And then it'll go ahead and skip straight to its fallback case. If and I guess this works like this. If we get to the point where we can actually pull it out, that's just a matter of rearranging memory on the buffer, right? If we have the cyclical buffer, we might have to just do, if it's split up, just do 2 mem copies to rearrange it. It's going to be like 40 bytes, so we're talking about fairly cheap rearrangements here of, you know, swapping characters around to get it in the right spot. We might need a temp space to swap it into, swap the head into here, and put the tail there, and there we go. We use that memory out of the temp space. I don't know, it doesn't matter. We then have the string we need to compare it against everything in the table. There's also nothing stopping us from building the hash as we go anyway, although that might be a bad idea because now we're doing work, we're volunteering to do work ahead of time that might not have been necessary. The only advantage to it is if we do it that way, we would be able to avoid the rearranging the cyclical buffer. But to be honest, we don't even necessarily need to rearrange the cyclical buffer, right? We could probably get the cyclical buffer to work without ever needing to rearrange if we just hard set to 0 every time. Like if our position in the buffer resets to 0, so it wouldn't be cyclical at all. It would be reset to 0 whenever we start a new token, and it would only be cyclical for when it overflows, which is the case when we don't need to rearrange it anyway, because we're not going to look at it. So then the last question is, do we even bother to keep writing stuff out past the end, or do we just say, set a flag that's like, we're not filling the buffer anymore, or something like that? But we have options, right? So all of this is going to work out just fine for this setup. So there we go. That was an entire episode of playing around with looking at how this will look if we just write a basic version. So we didn't end up generating any code or even writing any real code. All of it was experimental in our head stuff, but now we've done an important step before we go to generating stuff, which is understanding what the stuff we're going to generate needs to look like. It's going to have this structure. So I'm going to save this here because we want to remember what we learned. Now, this is actually a structure for temporally chunked input with a control flow implementation. But we're actually doing this, so it's even going to be a lot simpler than this. But we've thought through so many details now that we're well equipped to go into writing the generator, I think. So next episode, we'll get straight into that. We will be writing a generator. We're going to write something that generates this, and hopefully get to see this working within the next hour or 2 of episodes. So thanks for hanging out, checking this stuff out, and I'll see you guys around soon. Bye.